All right, today we talk about many types of properties that we've been using for years. Most of them we've seen before, but some of them are kind of new. The first one, the addition property of equality. You'll see on your practice sheet that you've got a lot of room to the right to make some notes. What I want you to do is, if I have something typed in blue here, let's put those notes off to the side, because what the addition property of equality says in math words is this. We don't understand math words very well. We understand our words. It says that you can add or subtract the same number to both sides of an equation. So where you got room off to the right, if you just pause the video and get that written down, I'd appreciate that. Here's an example, which you don't have to write this down, but you've been doing this for well over a year now. If I asked you to solve for x, what would you do right here to solve for x? What would you do? Add 5 to both sides. And we don't even show these baby steps anymore, but isn't this what you do to solve for x? And the reason why you can do that is because the addition property of equality says that you can do that. Is that cool with you? It's totally legal to either add or subtract the same number to both sides of an equal sign. The next property I have for you is the multiplication property of equality. So this stuff in blue here, if you just write that over to the right, it says that you can multiply or divide both sides of an equation by a number. It says you can multiply or divide both sides of an equation by a number. And of course, you can't divide by 0. That's against the rules of mathematics. But it's just a little note. So you can pause the video and get that written down also. So here's some quick examples. If you looked at this equation, you don't have to write them down, but what would you do to solve for x? Divide both sides by 5 and get x equals 6. Didn't I just divide both sides by 5 right there? That's totally legal to do. And over here, if you had like x over 3 equals 9, isn't this a divide by 3 right here? How can we get rid of that divide by 3? You multiply both sides by 3 and get x equals 27. These properties are not new to us, just their names are new. It's like, oh, I didn't even know that was a property or anything like that. So you can either multiply or divide both sides of an equation by any number you want to. Now, your worksheet doesn't even have it like this anymore because I got rid of these, but the way our book works is the book uses something called the subtraction property of equality or the division property of equality. We will not be using those because those are redonkulous. Multiplication and division are the same thing. Division is multiplication. If I wanted to do 5 divided by 5, that's the same thing as taking 5, and instead of dividing by 5, if I multiply by 1/5, I'd get the same thing. There is no such thing as division. It's just multiplying by the reciprocal is what you end up doing. And there's no such thing as subtraction. If you wanted to do 5 minus 5, that's the same thing as saying 5 plus a negative 5. It's just adding negative numbers with positive numbers. So there is no such thing as subtraction in my eyes. There is no such thing as division. It's either going to be the addition property of equality or the multiplication property of equality. And I didn't even put these on your practice sheet, so you don't have to worry about those. Those you should have been pretty familiar with. Next one, new to us, the reflexive property of equality. Just write the blue information down. Okay, write the blue information down. The reflexive property of equality says A equals A, baby. A equals A. You see the exact same expression on both sides of the equal symbol. It's so simple that it's hard. The reflexive property of equality says you'll see the exact same expression on both sides of the equal symbol. You got 4 equals 4. Isn't that the exact same thing on both sides of the equal sign? You got measure of angle 1 equals measure of angle 1. And it seems so silly. It's like, why do you even need to have that? It's like, of course 4 equals 4. I mean, duh. Well, we'll see some great geometry examples as we go along this year. But reflexive. Doesn't the word reflexive sound a lot like reflection to you? Like if you saw your reflection in the mirror, what you see is what you get, right? Reflexive property to me, I kind of think of reflection, right? And what I see on one side is the exact same thing I see on the other side. Sound okay with the reflexive property? Now, the next one, we use all the time, we don't even know about it. The symmetric property. Here's what it says in blue. First of all, you got a typo on yours. Yours says if A equals B, then B equals C. It should say B equals A. Please change that little mistake on your symmetric property. It says if A equals B, then it should say B equals A. Pretty sure yours has a C right there. Isn't that correct? Cross out that C and put an A. Here's what it says. It says it's legal to switch expressions from one side of the equal sign to the other. Pause that video and get that written down in blue off to the side. And you'll notice I have a word in different color, switch. What letter does switch start with? Starts with an S. What letter does symmetric start with? S. They both start with S. Symmetric means switch. Symmetric means switch. We do it so often you wouldn't even realize. What if I told you to solve that equation, right? What would you do to solve that equation? Subtract 3 from both sides, right? And the addition property of equality says we could do that, doesn't it? Then you'd be left with this. And if I asked you what you got, I really doubt that anybody would ever say 2 equals x. What would you say instead? What do you say? X equals 2. You automatically make them switch sides. Don't you really just do that? It's like, I don't want to say 2 equals x. Isn't x equal 2 the same thing? What was on the left was on the right. What was on the right was on the left. You made them switch sides. Well, the symmetric property of equality says that you can do that. We do that all the time. So just like this, if y equals mx plus b, then mx plus b equals y. I want you to notice something, though. They give you 2 statements, right? We skipped some stuff in Chapter 2 about if-then statements. This is called the hypothesis, and this is called the conclusion, right? Aren't there 2 different equations right here? Y equals mx plus b, and here's a totally second one right here, correct? Do you see what was on the left side was a y, and now it switched over to the right side in the other section right there, and then vice versa? So you have to see 2 different equations for it to even be the symmetric property. If I gave you this, how many equations do you even see? 1, right? That cannot be the symmetric property because it's like, how can things switch? This is the reflexive property right here. You've got the exact same thing on both sides of the equal sign. A lot of people are like, well, isn't this like the exact same thing on both sides of the equal sign? Yeah, but you had 2 different statements to start with, and from the first statement to the second statement, then they make them switch sides. So here's another one. If x equals 2, then 2. I couldn't even say it. That's the second time. Friday I couldn't say it right. I underlined that. I said x equals 2 right there. I can't even say 2 equals x because we're not trained to think that way. Aren't we trained to say x equals 2 in the first place? But that's a symmetric property. Like I said, hang in there. It's blah, 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 blah. Once we start putting these into action, it'll make a lot more sense. Are we okay so far, though? Next guy. This one's a big one. Put an asterisk by it, man. We'll use this throughout the whole school year. It's a transitive property. Very, 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 very often. First, I want to explain it before we write down what it means in our own words. Here's our hypothesis. Isn't all of this right after the word if, correct? They gave me 2 different statements in the hypothesis. They said A equals B and B equals C. You have to know those 2 things. Cool? Now, in this information that I underlined in green, out of these 2 equations, was there anything common to both equations? What's common to both of those equations? Isn't there a B in this equation and there's a B in that equation? Well, the transitive property says that we could totally do this. In our hypothesis, didn't we have A equals B? You don't have to write this down yet. I'll tell you what to write down. Our hypothesis said A equals B and B equals C. And notice how I wrote them on top of each other instead of like side by side instead. It's so much visually appealing if they were on top of each other. Here's what we can do. We could say, hey, boop, boop, peace out to you, things that were in common. Wasn't B in both of them? What's left over? A equals C. Then here's what we will, then we conclude that A equals C. So here's what I want you to write down. I don't have it nice and typed out for you, so I'll just tell it to you. Write this down. Here's what the transitive property says in our own words. We can cross out what's in common. We can cross out what's in common and write the leftovers equal to each other. We can cross out what's in common and write the leftovers equal to each other. Let's see if we can use the transitive property in a geometry problem. I'm giving you some information right here. Check out these 2 things. Measure of angle 1 equals 30 degrees. Measure of angle 2 equals 30 degrees. First of all, do you see anything common to those 2 statements? Isn't there a 30 degrees in both of them, right? So the transitive property says, peace out, Girl Scout. You can cross those out. And then what would you have left over? Measure of angle 1 should equal measure of angle 2. You don't have to write that down, but it's pretty obvious. If the measure of angle 1 is 30 degrees and the measure of angle 2 is 30 degrees, shouldn't the measure of angle 1 be the same as the measure of angle 2? We will use this more often than you can shake a stick at. I don't know why you're shaking sticks at stuff, but we'll use it often. Next. Here, I also told you that they're all of congruence. It just depends on what symbol you're using. We'll kind of see that as we go through the proofs. But let me show you a visual of where the reflexive property will come in. Just watch this, baby. Check this triangle out right here. See that green triangle that I highlighted right there? And then check this guy out, this blue triangle that I highlighted right here. Is there any segment that I highlighted both blue and green at the same time? Segment AC, isn't it shared between both triangles? It can't be 4 inches in one triangle and then 3 inches in the other triangle. It just doesn't work that way. Wouldn't segment AC have to be the same size as itself from one triangle to the next? Segment AC has to be congruent to segment AC. Otherwise, the whole world just blows up in our face. If it's 4 inches in one triangle and 3 inches in the other triangle, it just can't happen, right? So this is the reflexive property of congruence, where a segment is the same size as itself from one picture to in the same picture. And we'll see that when we get into chapter 5 for show. A couple more basic properties. Substitution property. You don't even have to write anything down. It's so stinking obvious. You used it throughout your whole life. We used it on the previous test. If I told you x was 4, y was 3, and z was 2, correct? Use the substitution property to simplify this. That means anywhere I see an x, what can I do? Now, some people say put 4 in. A lot of people say plug it in. And I got a question for you. Is the name of this property called the plug it in property? What's it called? Substitution. That's just learning to speak, because remember, we've got to justify all our answers. And we can only justify our answers with 3 things: a definition, a postulate, or a previously proven theorem. Well, when I say, what do you want to do? If x is 4, what do you want to do? And you say this, well, let's just plug that in. And I'll say, what? And you'll say, well, I just want to plug it in. And then I'll say, what? And you'll go, well, I'd like to plug it in, because you don't think that I can hear you or something, because I keep asking you what you want to do. And I'd go, what? Because I can actually hear you, but you don't understand that I'm trying to get you to say, I don't want you to say plug it in. What do I want you to say? You want to do what? We want to substitute it in, because when we justify our answers, we sure as heck don't plug it in property, right? It's called the substitution property. You with me? So it happens every year. I have to do that. What? People think I'm like Little John for a little while, but it's like, that was cool in 2002, What? Actually, 2003. So we know about substituting stuff in, right? By God, please tell me you know what the distributive property is. We know what that's all about, correct? And here we go. These you don't have to write down either. I told you 3 things all the time because I'm right, but our book calls it 4 things. They call these 2 separate things. Postulates and properties are almost like the same thing. So I just say definitions, postulates/properties, or previously proven theorems are the only things we can use to justify our answers. And today, we finally start doing some proofs. And we're going to start really, really simple with algebra proofs. We do what's called T-chart proofs. Do you see how this chart that we're going to put them in looks like a capital T? That's why it's called a T-chart proof. Organization is the most important thing in any kind of proof. You're writing this down so somebody else can read it, preferably me. But you want to be able to hand it to anybody, and they should be able to read it. So they have to give you something, and then they have to tell you what they want you to prove. Sound cool? So here's the very first thing you do in any proof. You start with step number 1. We always have to label our steps, and you start with what they gave you. What did they give us in this particular problem? D equals 20t plus 5. That's what we put. And put a little tail on your t so it doesn't look like a plus sign. But that's what they gave me, right? There's our most basic equation right there. They gave me that. I need a reason for that. Well, there's only one reason where this came from. Didn't they stinking give it to me? Correct? So reason number 1. It also has to have the same step number. They gave that to me. There's your first step in every single proof. You read the given, then you copy it down in the chart and justify it with a given. Need a step 1 in both spots. Sound cool? So you read the given, and you write the given, and you justify it. The next thing you do is look at what you want to prove. They want us to prove this. Would you kind of be of the believing that they want us to get t all by itself on one side of the equal sign? So let's do that. They're asking us to solve for t. We're just using algebra. Could you tell me what's the first step you would do to get t all by itself? What would we do to get t all by itself first? Subtract 5 from both sides, right? Let's do it. I don't need to show the baby steps, so let's start with step 2. If I subtract 5 over here, wouldn't that become d minus 5 equals 20t? Is that cool with you? Now, all I need is a reason of why we can subtract 5 from both sides. From all that junk I just gave you in the blah, 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 is there any particular reason why I could subtract 5 from both sides? The addition property of equality says so. So now step 2 lines up perfectly with step 2, and wasn't it called the addition property of equality? If I abbreviate something, you can abbreviate it. Addition property of equality is how I like to abbreviate it. Everybody knows that add means addition. Prop will mean property, and of equality. You got to put that because there's also properties of inequality. Remember solving stuff like this, 3 is greater than 2 plus x, where you have inequalities instead of equalities, the greater than and the less than stuff. So you got to put of equality because this was an equation. Rock and roll. Next step. What would we do next to get t all by itself? Wouldn't you divide both sides by 20? Now normally we do that to all 3 terms. But you see what they did right here was they just did a divide by 20 and a divide by 20 like that right there. You with me on that? So that's what we'd get. We'd get step 3. D minus 5 is all over 20. And wouldn't that equal a t? How come I can do that? Why can I divide both sides by 20 legally? That's the multiplication property of equality that says we can do that. I know it's weird because it's our first proof, but how are we feeling so far? Feeling all right? Okay? And now I got to look. They wanted me to get this. Did I get that? It looks like it, but the answer is not quite yet. What's wrong with this one encircled in green versus that one? T's got to come first, so can I make them change places? Step 4. T can come over here. D minus 5 comes over there, over 20. And all I need to know is why I can make them switch sides from one to the other. How come that can happen? And you will not abbreviate the word symmetric. That is new to us. Symmetric property says we can do that. And there is no symmetric property of inequality, so it's just called the symmetric property of equality. My bad, because there's one of congruence also, isn't there? Symmetric property of equality. You feeling okay with our very first algebra proof right there? What I want to do is, so as we go to the next one, our first step is to always read the given, write the given. So let's do it. They give me 8x minus 5 equals 2x plus 1. Right? What's the reason for that? They gave me that. Step 1, step 1. Always the same. Those are free points right there, baby. Each one of these steps is worth a point. Cool. They want us to prove that x equals 1. Aren't they basically saying, please get x all by itself? So there's many ways we could do it. Couldn't we add 5 to both sides over here, or we could subtract 1 from both sides, or we could subtract 8x, or we could subtract 2x? I could care less which way you do it, but I'll tell you which way I always do it. I first move all my x's to one side. And which side do I really want them on, the left side or the right side? Don't I want them on the left side over here to finish this off? So what do you want to do first? Let's subtract 2x. You don't have to do that, but that's what we're going to do. So 8x minus 2x is 6x. The minus 5 comes down, the equals comes down, and you're just left with 1. You cool with that? Justify. How come I could do that? Why could I subtract 2x from both sides? The addition property of equality says so, baby. Righteous? Next move. What will we do to continue our path to get x all by itself? Add 5 to both sides, so step 3. And the reason why I can add 5 to both sides is the exact same thing. You're adding the same number to both sides, so that's the addition property of equality also. And now to get x by itself, we still have to do something. We got to do what? Divide by 6 to both sides. And the reason why we can do that is multiplication, property of equality. Did we prove what they wanted us to prove? You bet, man. Let us go to the backside. Let's read the given, write the given, and then since we have a picture, we should also mark the given in the picture. So read the given, write the given, mark the given. Let's get that done. Are we cool with the first step? So we're marking with tick marks, and I'm pretty sure your paper already had them on there. The next step is kind of weird. I'll just talk you through it. Here's what we want to do. We want to say step 2. This says that the segments are congruent, correct? Well, look what we're trying to prove something about. Aren't we trying to prove something about equality right here? So that means I got to do a switch over. I got to switch from this statement to be in segments congruent to instead say the distance from D to F equals the distance from E to G. That's the next step that I got to move. I got to somehow make the move from congruence to equality because they wanted me to prove something about equality. Let me ask you this. If things are congruent, doesn't that mean they're the same size, same shape? If these segments are the same size, same shape, shouldn't the distance from D to F be the same as the distance from E to G? Shouldn't that be happening? The reason why is because that's straight up what congruent segments means. That's the definition of congruent segments. And you'll see how I abbreviated definition, which is called that a DEF. I didn't even write the word congruent. I just used the symbol. But that's what congruent segments means. If segments are congruent, it means that they're the same length. That's the definition of congruent segments. And this right here says they're the same length, a.k.a. their distances are equal. Are we cool with that so far? Just the basic setup. That was a weird step right there. Next thing. What could I end up doing? Any ideas? You said we wanted to do some substitution. So step 3, distance from D to F. Don't we know that as 11 right here? So that'll go in that place. Equals comes down. Do we know the distance from E to G? It's 2x minus 9. And you said that we could do that for what reason? Why could we replace those? If we use the right word every time, we don't even have to think. Isn't that the substitution property right there? So substitution. You will not abbreviate it. People can't spell it right, so we'll learn to spell it. Substitution. And you don't even need property after that for all I'm concerned. That's just called substitution. Got a question for you though. What if I would have wrote 2x minus 9 right here and 11 over here? Would that be legal to do? Well, is the distance from D to F 2x minus 9 according to what they told us? It's got to be right underneath, right? They got to correspond to each other. The 11 corresponds with the distance from D to F and likewise. You with me on that? Cool. Solve for x. You and pal get the rest of this proof done. Justify every step as you go. So pause the video. Get that done. Add 9 to both sides. The reason why I can do that is the addition property of equality. Correct? Then what would I do? Divide by 2. The reason I can do that, multiplication property of equality. Looks pretty good, but not quite what they wanted. I got to make them switch sides. What says that I can make them switch sides? Symmetric, which you cannot abbreviate. Property of what? Of equality. Uno más. Read the given, write the given, mark the given. Read the given, write the given, mark the given. So, step 1, angle Y is congruent to angle Z. Reason given. I read it, I wrote it, now I got to mark it. How in the world do I go up to that picture and mark angle Y congruent to angle Z? Arc marks up there, baby. So, boom, boom. Lots of points that we miss for not marking stuff. It'll make sense once we get to more complicated proofs of why you're going to need all these markings. Okay, so read the given, write the given, mark the given. Now look back and see what you do to step 2. Don't you notice they want you to prove something equal, but you started with congruence? So see if you can compare this step 2 to the previous step 2 and get that written down. Give it a shot with pal. So if the angles are congruent, that means that their measures are equal by the definition of congruent angles. Now from here, you should be able to rock and roll with this. So get this puppy complete. Prove that x equals 100 one way or another. Very similar to the previous proof. Pause the video, get that done. Purpose. So I substituted in, then I subtracted x over this way. You could have went the other way. It doesn't really matter. It's whatever you wanted to do. And then I added 90 to both sides, and then I finally made them switch around with the symmetric property of equality and etc. But one way or another, you just got to justify what you do. There's no perfect way to get it done. These three steps have to be the same right here, and then from there it depends on how you solve your equation. You just got to have the right justification. Cool? All right, there's a typo on your homework. If I have given it to you, if you look at number 2 on your homework, it says prove negative 7/6. That should say prove r equals negative 7/6. So on number 2, the prove, say r equals negative 7/6 is what you need.